Hey everyone, we're going to do a quick video about section 11.7, which isn't a section with new convergence or divergence tests, but rather is a section where we try to discover strategies for knowing which convergence or divergence test to use and what to look for when determining whether a series converges or diverges. So let's go through all the tests that we know. For the divergence test, well, first of all, we're looking at a series from 1 to infinity where we've got some general term an, and we're interested in whether that limit of an as n approaches infinity is 0 or not. If it's 0, then we don't know, right? We can never test for convergence with this. However, if the limit as n approaches infinity of an does not equal 0, then the series diverges. Geometric series. Well, that's the series where we're talking about the sum from 1 to infinity of a times r to the n minus 1. Series converges if the absolute value of r is strictly less than 1, diverges otherwise. For the integral test, we also have our generic series. We'll call it an. Perhaps you can call it f of n if you'd like. But it converges, remember, if and only if the integral converges, right? So we consider the improper integral from 1 to infinity of ax dx. And if that converges, then our series converges. Similarly, the series diverges if the improper integral of ax dx diverges. P series is a pretty straightforward looking series, right? We've got the sum from 1 to infinity of 1 over n to the p. Series converges if p is greater than 1. Diverges otherwise. The comparison test, well, the comparison test is, that requires a little bit of work, right? Because you've got a series with a general term an. If we can find some term bn that's greater than or equal to an, and the sum of bn converges. Or if we can find some series bn that's less than our generic term, our general term an, and the sum of bn diverges. All right. Limit comparison test is the same sort of thing if we have that the limit as n approaches infinity of an over bn equals some constant, equals some constant that's not 0, and the sum of bn converges. Let's move that over here. Similarly, the series is going to diverge if, well, I'm just going to copy and paste this over here. We have the same thing, except that series we were comparing it to diverges, right? And we have the same situation as before. Alternating series. Remember, this is a test only for convergence. No such thing as a divergence test. Here, the series has the form 1 to infinity of -1 to the n, or something like that, times an. So the convergence test is twofold, right? We need to ensure that an is monotone decreasing, which means that an plus 1 is strictly less than an. And we also have to ensure that the limit as n approaches infinity of an equals 0. And it might seem silly and excessive that we have to do both of those, but we do. Okay. Now for the ratio test, that was the one that we recently learned, right? We learned that today, in fact. The ratio test is a test for absolute convergence or divergence. Right? Again, we're looking at our generic series. from 1 to infinity of an, and it converges if the limit as n approaches infinity of the absolute value of an plus 1 over an is strictly less than 1. Diverges if the opposite happens, right? Limit as n approaches infinity, absolute value of an plus 1 over an is greater than 1. Remember, if the limit equals 1, then we don't know. We shouldn't use the ratio test. It might converge, it might not. We need to use another test. The root test is very similar. We take the limit as n approaches infinity of the absolute value of, in this case, the nth root of the absolute value of an. So I'll call it to the 1 over n. Right? If that is less than 1. Whereas we have a divergence series if we take the limit as n approaches infinity, the absolute value of the nth root of an, and we get something greater than 1. Those are all the tests we know, and that's a rough sketch of when they test for convergence, when they test for divergence. Now let's just go through a quick little thought process to try to get some idea of which test we would use and when. If we can look at our series and notice that it's got this form, well then we're going to use the geometric series. You could also use the ratio test, but keep in mind that the geometric series is a little bit better usually because number one, it's a bit more straightforward. Number two, you can actually determine what the series converges to, whereas you can't do that with the ratio test. For C, if you're able to see that your series equals 1 over n to the p, then you're going to use the p-series. Or if I ask you to prove it for some reason, then you'd use the integral test. Now, if you have something similar to one of those two series that you saw above, then you could use, actually, just because you could also use the comparison test with the integral test, I'm going to call this the integral test. Right, so anyway, if you have something similar to one of the things above, then you would use either the comparison test or the limit comparison test. The other thing you can do, and in fact, you can do this first. If you're good with your limits, it's a pretty quick one. If you take the limit as n approaches infinity of your general term, it's not 0, then your series diverges by the test for divergence. Done. Little typo in the notes. It should be if the limit does equal 0, then we don't know. Use another test. Okay. Now, obviously, if you can turn something into an integrable function, I should also point out that it is positive, continuous, actually maybe I should say here, it's positive, and can be turned into a continuous integrable function. Maybe I should say continuous decreasing integrable function. Then we use the integral test. Okay. If the series is alternating, then it's not necessarily the alternating series test, although it certainly could be. It could be geometric. It's possible. Probably not. But don't just think, oh, negative 1 to the n, it's got to be alternating series test. It could be geometric. Look a little harder. All right. It could also be the ratio or root test. Remember, those terms don't care about the alternation because they take the absolute value of your term. You're comparing things proportionally or exponentially. If you've got a term c to the n factorial, or n to the n, then you're using the ratio test. And of course, if a series is raised to the nth power, then you use the root test. That's usually kind of observable. Not always, right? Be a little careful. So here is a list of a bunch of infinite series, and you need to figure out whether they converge or diverge. And what test would you use to figure that out? And bonus, if it does converge, then is it conditional or absolute convergence? So on this page, we're going to just say what test we would use. And then on the next page, we're going to actually do them out. Now, I'm not actually going to do them out. I'm going to leave that one to you. But let's at least take a look at which series test we might use. Well, for number 1, you see an exponential with a polynomial. That's a green light for the ratio test. And I think with some intuition, you should notice that 6 to the n grows much, much quicker than n. So it should diverge. Here for number 2, it's alternating and it's monotone decreasing. It looks like the limit of the term is going to 0, so looks to me like we should use the alternating series test. And I believe this should conditionally converge. Remember, it's extra work to show that the absolute value of the term diverges. You might want to compare that to a p-series. Number 3 might be a little bit tricky, but use the comparison test. Remember the upper bound of arctangent, even as n approaches infinity. And that really looks to me like it ought to converge. Number 4, I remember first seeing this one. This one hung me up for a little bit. But it turns out you can use the LCT. Try a clever comparison maybe to something a bit more familiar. Number 5, as complicated as it is, you could turn this into a geometric series. And looking at it, it looks to me like it should converge, I believe. By the way, for this one, number 4, it's a divergent series. Right? Last but not least, number 6, I hope that's clear. We see a factorial that's ratio test all the way. And I'm not sure if it's immediately obvious, but that one looks to me like it's going to converge. Actually, I take that back. I believe it's going to diverge. So maybe it's not so obvious. And actually, looking at this a bit more, I'm not totally sure. No, I think it's actually going to converge. I lied. Right, try to prove me wrong on that one, but I believe this will, wait a minute. No, you can reduce that one. You can reduce that term by quite a bit, and it is, in fact, going to diverge. Sorry for that little hassle there. But again, this is not what you should be doing. You should just be seeing which test you can use, trying to gain some intuition, and then doing it all out. Alright, so for each of these, I'm going to let you try it. Maybe let's take a look at number 6, just because that was giving us a little bit of an issue here. Even though we're doing it out of order, I think that's fine. First of all, note that this equals, let me move this a little bit up here. Note that this equals the sum from 1 to infinity of 2 to the n times n factorial, and then this is a little bit clever here, times n plus 2 times n plus 1 times n factorial. So what that means is we can cleverly cancel out that n factorial. And now I think we can see that we should use the ratio test. All right, the limit as n approaches infinity the absolute value. I like to write it just to remind myself. 2 to the n plus 1 over n plus 3 times n plus 2 times, and then this is going to be n plus 2 times n plus 1 on the top, 2 to the n, right, we multiply by the reciprocal. This is going to be really quick because I want you to ensure that this is true, but the stuff cancels. And you wind up getting 2, which is greater than 1. So the series diverges. Now I'm just going to go ahead and move this to the bottom. Try doing the first 5 on your own. Remember, we'll do these in class together. In fact, we'll do the whole thing in class, but see what you can get done.